Hello everyone, welcome back to your once per week systems design video. I am Jordan. So today I'm going to try and make it through this thing in one take. However, I did eat like 4 Quest bars at work and I am currently sitting in the smell of my own farts. Now, not to say that I'm running out of memory or anything, but I have been garbage collecting a lot and I may need to take a heap dump. Anyways, let's go ahead and get into this thing. So today we are covering TicketMaster. I've said it before, I'll say it again, I don't like this problem. The reason being it's freaking ambiguous. Anyways, let's try and get into it and I can try and deal with the ambiguity. So TicketMaster, if for whatever reason you don't have it in your country, I'm actually not sure if it's just American, is a site where you can buy and sell tickets for concerts or shows or any other sort of venue event that sells them. So for example, if we've got ourselves a Taylor Swift concert, it would basically have some layout of the map like so, where you've got your stage in the middle, and then a bunch of different sections with the seating prices within each section. So, you know, Taylor Swift is pretty hot right now, and those tickets are going for a lot of money. As a semi-Swiftie myself, I don't think I will be investing. So let's do some problem requirements, which again are pretty ambiguous for this type of site because they don't all work the same way. But, okay, number one, like I mentioned, they're just going to be events that we can go ahead and buy tickets for. Number two is going to be that upon clicking for an actual seat that you want, you can make a claim to it, right? So when I say I want to get seat X, I have 5 minutes to go ahead and purchase seat X. And so the issue with this type of claiming behavior is there are a few different ways of implementing this, and I don't mean in technology, I mean like in terms of behavior. Like when I claim it, is it going to be the case that everyone else can just like jump on that ticket after I give it up? Or is it going to be the case that, you know, we have some sort of wait list for doing so, or are we not going to do any claiming at all? Who knows? I certainly don't, but I'll try and cover everything. Okay, let's do some very crude capacity estimates. As the sleuth that I am, I actually went to TicketMaster and checked out how many shows there were in New York City. And there were around 4,000. So scaling that up to around the size of America by population, that would mean there's probably around 100 to 200,000 events at one time that we can purchase tickets for. And so let's really ballpark this thing and say, imagine each event has 100 different sections that tickets can fall in, and each section has 100 different seats. If I now went ahead and assumed that every single seat could be represented by the following tuple, right? The event ID, the section ID, the row ID, and the actual seat number. And then also, like I mentioned, we want to be able to claim this thing and then subsequently book it. So something like a claim user ID and maybe potentially a Boolean as well to just say whether or not it's actually been booked. But again, if we're just assuming the above, that's basically 5 fields where each of them can be modeled as an integer, and if so, that's 4 bytes per integer, totaling 20 bytes, and then again, we're going to multiply that by the number of events times the number of sections times the number of seats. So we only actually have to store around 20 gigabytes of data at a time for our seats that are bookable. You know, obviously for historic bookings, we're probably going to have a lot more data than this over time. But the point is, if we're actually only trying to service users for active events, we don't actually need that much storage. And so what we're going to talk about later in this video is the potential utility of doing so in memory, because we're going to want some slightly more complex functionality depending on how we want to do these ticket claims. And yeah, we'll get into that in a bit. So like I mentioned, probably more for historic bookings, but you know, we can just use a normal database there, keep that all on hard disk. Okay, so let's discuss some actual possible approaches to how we want to deal with our problem. So I'm going to discuss 3, and I will probably ditch the first in a second, and then we'll mainly discuss the last 2 in this video. So the first is, the first thing is that I mentioned the problem's ambiguous. I mentioned that we want to be able to claim a ticket, but how can we actually do so? So the first could be that, you know, we just claim tickets after we pay for them, right? I pay for one, now I have it. If me and someone else are trying to pay for a ticket at the same time, whoever enters our payment information and clicks that confirm button first is going to win. So this could work, but at the same time, it's probably a pretty bad user experience, right? Because I'm not going to figure out that I didn't get the ticket until I've already done all this work. Maybe I had to sign into my account, maybe I had to enter my credit card information. And so generally speaking, I do think a lot of these like ticket selling sites do not actually work this way because of that inconvenience. So we're probably not going to go into this one too much. If we did, it would be pretty simple. Go to a database, whoever writes first wins. Grab a lock if you have to, whatever. Number two is that tickets are going to be claimed with a TTE, or a time to expiry, before we actually buy them, right? So I say, oh, I want to go to the Taylor Swift concert. I see a couple of open seats. I click, I want these seats, and now all of a sudden I have a 5-minute timer where I can go ahead and check that out. So that's great, but it also does actually have some downside, which is that if all of a sudden I take longer than my 5-minute allotment, now all of a sudden anyone can make the next claim. It's possible that someone else, was thinking about purchasing that ticket first, but now all of a sudden you've got 5 other people trying to get it at the same time. And of course, when you do have a bunch of other people trying to do something at the same time, we can run into thundering herd problems in our actual backend. So we'll have to discuss those as well. The next thing is that if we want to make this more fair, right, where, say I'm in line to get a ticket, I drop out, the next person in line actually gets them rather than some other rando who jumped in. What would be great is if we could have some sort of wait list, right, a FIFO wait list. So FIFO just means first in, first out. If I get there and then you get there behind me and then a third guy comes behind you, you have priority after I drop out. So again, this is going to be the most fair, but it is also not so easy to implement. We're going to discuss some of the caveats associated with actually doing that, and we'll go through them. So the first thing to actually discuss is this kind of unfair claim, right? Because I mentioned that the option 3 was the quote-unquote fair one, so I'll call option 2 unfair, and I'm not going to cover option 1 because I think that for the purposes of a systems design video, it's pretty trivial. Okay, so option 1 is going to be that unfair claim, right? Where whenever I express interest in buying a ticket, assuming that no one else has a claim on it, I can actually have 5 minutes to go ahead and check it out. So the first thing that's going to happen here is I can claim seat 9 and 10. User 2 afterwards can try and claim seat 10 so that he can go check it out, and then the database is going to say no, user 1 already has a claim on that. So a couple things to note right here, right? We are going to need our rights to be both atomic and serializable. The reason being that, if I try and submit a claim for both 9 and 10 and only the claim for seat 9 goes through, well, that's no use to me because then someone else can check out seat 10 in the meantime. Additionally, if it is not serializable, I could submit a claim for seat 9 and 10, and then somehow, like in the middle of that, basically this guy's claim for seat 10 could go through, and now all of a sudden I have a split claim, which isn't going to work. When I claim seats, I want to either be able to get them or I don't want to be able to get them, and it's that simple. I should get all or nothing. Cool. So the way that we would do this with modern databases, assuming we didn't want to implement all of that locking on our own, is probably by using a transactional database. Now, the ones that are typically going to be implementing something like that would be SQL databases. You could use MySQL or Postgres or something like that. Some of the NoSQL ones do have them, but let's keep things simple here because we don't need any crazy write throughput, at least for the moment. That being said, it is still possible that we do want to increase our write throughput, right? Like it is going to be the case that certain events are going to have a lot of traffic. And if that's the case, something like partitioning might actually be able to help us distribute our load over multiple partitions so that that way one database node isn't getting completely overloaded. So again, the idea is we have all these transactions so that we want to avoid like partial claims like I was mentioning before. But the issue is if we're dealing with partitions in order to help reduce our load on every single partition, now we run the risk of actually having a distributed transaction, right? If seats were on 2 different partitions and I wanted to make a claim on seats that were in 2 different partitions, that would be bad. So how could we avoid this? Well, actually, we could go ahead and basically make it so that every single row is on the same partition, right? Because if I know that I want to book 2 seats, and I'm always going to be booking 2 seats within the same row, having a given row on the same partition is going to allow us to avoid distributed transactions. So hopefully that makes a decent amount of sense. Distributed transactions are slow because they require us to do a 2-phase commit, and that is going to be very bad. We have to coordinate basically between both partitions and go back and forth twice over the network, which is not ideal. So again, like I mentioned, this guy could be on 1 partition, and maybe it's, row 2, row 3, and row 6 are on partition 1, and then row 1, row 4, and row 5 are on partition 2, or something like that. We can balance them out. So let's continue to talk about partitioning a little bit because it's not so simple as I've just made it seem. Like I mentioned, we want the key to be some combination of the event ID, the section ID, and the row number, and then basically we can take some hash of that and then use the actual hash range of it to try and partition the rows relatively evenly, right? So that there are a similar number of rows on every single node. By using consistent hashing, we can ensure that not only are there similar numbers on every single node, but that if a node were to go down or a node were to be added to the cluster, we would ideally have minimal rebalancing. So again, not all rows are going to be equal. Unfortunately, like with most actual systems, we can have hotspots, right? A Taylor Swift concert at the end of the day is going to be a lot more popular than the example I used right here, which is the Dogecoin Summit in 2024. I wouldn't think there are too many people going to that. So again, how can we handle the fact that certain rows are going to get a lot more users that are interested in them? Rows or sections, we could partition by section as well if we wanted to make them a little bit less granular, but the idea is the same. You know, if I just post a Taylor Swift concert, the first, 20 or 30 minutes, there might actually be a ton of traffic there. Well, of course, the general idea is if we have a certain node that is going to be overloaded, option one is going to be we can, repartition on that row, right? So we would take, say there were 10 rows on that partition already, now we take 5 of them and throw them on a different partition. So that's an option. And then the other, which I also think is pretty compelling here, is to actually use a write-back cache. So like I mentioned, for these kind of hot rows, we tend to know in advance, right, which ones are going to be popular. I know right after posting like a Drake concert or a Taylor Swift concert that it's likely that thing is going to be hot for a little bit. And so this actually provides us with the opportunity to basically route all of the requests for that node to a specific cache instance, right? I could put it in Redis or Memcached or even just a dedicated server, but putting it in memory is going to allow us to speed up those requests. So basically, like I mentioned, we probably know which rows are going to be popular in advance, and then from there we can go ahead and do our write-back caching. So we can basically just have Redis answering all of our claim requests, and then asynchronously in the background, once our bookings are completely done, right? We can do both the claims and the bookings on Redis, and then in the background, asynchronously, we'll go and throw everything over to our SQL database. Now keep in mind that Redis is kind of weird because it's single-threaded, so I'm not actually too sure how this would work in practice, but maybe rather than Redis, I'll just say arbitrary in-memory server with some amount of locking, which might speed things up in comparison to Redis, which is single-threaded, but we would have to test this out in reality. And then again, we'll sync all of that data to our database eventually when traffic dies down a little bit. Cool, so the write-back cache would be temporarily our source of truth. Okay. Now let's talk about another aspect of this kind of unfair claiming behavior, which is going to be claim expiration, right? So if you recall, I mentioned that after a certain few minutes, if I don't actually go and check out, my claim is going to expire and I won't be able to actually grab those tickets until I make another claim. So how can we go ahead and do this? Well, for starters, we definitely don't want the claim expiration triggered by like an additional networking request on the client device, right? Like the client device isn't going to be like, hey, I've waited 5 minutes, now I have to go back to the database and say, hey, it's been 5 minutes, I no longer have this claim. Why? Well, for starters, client devices may no longer be connected to the network, they may no longer be connected to our site, they may be malicious and not want to expire their claim, all of which would be pretty bad. So another option we could use potentially is a stored procedure, right, where I invoke some function on the database itself, and I'm actually not sure which databases would even support this type of thing, where 5 minutes later it goes and cleans up your claim. Which I think is probably going to be the easiest in this case, is just whenever I make my initial claim, put an expiration timestamp on the database, which is 5 minutes later. And that expiration timestamp, of course, will have to be generated by the database itself. Otherwise, malicious clients could just, put a claim there that's, forever in the future. So I write to the database saying, give me a claim. Database says, okay, what's my current time? Let's add 5 minutes. That's when this expires. So imagine we have the following row in a database, right? We've got for seat 22, user 40 currently is the claim. The claim's going to expire at 4 o'clock, and we're not currently booked. So the combination of the claim user ID and the claim expiry is itself a fencing token, right? So we've discussed this a little bit in my systems design concepts video, but the point is a fencing token is basically extra data that you can pass back to the client so that when they eventually try and go do something else later, we can validate that they are the proper client that should be making this request. So I'll demonstrate that in a second. Basically, initially, user 40 is going to make this claim. to the database, and the database is going to say, okay, your fencing token is 40, 4 o'clock. Meaning when you actually want to book those tickets, you're going to have to pass me back 40, 4 o'clock, or else I know that it's someone else trying to book these tickets and they don't actually have the proper information, right? No other client is going to be able to read this row directly from the database. We're just not going to expose it from the server as an API request. And so as a result, when I say 40, 4 o'clock, I know that we should actually be able to book this row. Okay, so request number 1 is going to be, user 39 says, hey, wait a second, I had a claim expiring at 3:59. Guess what, buddy? Your claim is expired, so it's not going to be you who's booking it. You can also have a malicious client saying, oh, I'm user 39, but my claim expired at 4 o'clock. Sorry, Charlie, not going to work. And then, same thing with user 40. Even though he currently has the claim, this is basically user 40 coming back later and saying, oh, I actually had this old claim, like let me book. No, we're not going to, because the current claim is something different, right? It expires at 4 o'clock now, and yours is from the 3:55 iteration, so no luck, sorry. Eventually, when the user comes along and he says, hey, I'm user 40 and my claim expires at 4 o'clock, we can go ahead and match these two up, say, hey, this thing looks good, and then switch our no to a yes. We're booked now. So hopefully that makes a little bit of sense. Cool. So, like I mentioned, what are some of the issues that we have when trying to deal with these kind of unfair claims? So basically, number 1 is that if I myself do not have a claim and someone else does, but I want it, I don't really have any way of knowing that I don't have the claim unless I'm pretty much spamming the database, figuring out whether or not I got the claim successfully. So spam is going to be number 1. Number 2 is that let's imagine that we can fix our spam by having the database tell everyone in real time via some sort of long poll or some webhook or some server sent event when the seat is actually unclaimed again or when the seat claim has expired. Well, that's not particularly ideal either, because all of these guys are going to get that message at the same time, and then they're all going to try and stake their claim, which, like I mentioned earlier, is going to be a thundering herd. So if I've got 100 people here and they all want to make the claim, now all of a sudden we just incurred a crap ton of load on our database and we could bring it down. So ideally, rather than just having this free-for-all whenever a claim expires, what would be a lot better is if we had some sort of wait list, right? Where we've got, user number 1, user number 2, and user number 3. And when these guys all find out that the thing is open, well, guess what? User number 1 is still the only one who's allowed to book. So ideally, that would make things a little bit easier. However, fair claim is itself also not that simple, because of the fact that now we have to actually care about the dependencies of people's claims. So let's go ahead and figure out what this slide is talking about. Basically, let's imagine we have 2 seats, right? We've got a seat 1 on the left, seat 2 on the right. And we've got user 1 that's claimed seat 1 and user 2. So this is user 1. This is user 2 on the right. And so what's now going to happen, basically, is we say, okay, user 2 is going to drop out, right? And so our priority ordering was that user 3 claimed both seat 1 and seat 2 after user 1 and user 2 did. And then the last thing that happened was that user 4 went ahead and also staked their claim on seat 2, but implicitly, they're waiting behind user 3. So they're actually dependent on user 3 to finish, assuming that we are respecting FIFO ordering. Now the problem is that user 1 is not done booking, right? So user 1 can take forever to book, or however long it is until their claim expires. And in a real crappy situation, what would happen is, not only just user 1 was staking on claim 1, but we have a whole chain of users over here. And then this guy, rather than directly staking on seat 1, basically staked his claim behind all of these guys. So now he's first in priority over here and fourth in priority over on the left. And so the question is, does user 4 have to wait for user 3 to completely drop out until he books? Because that could be a while. Or does user 4 just get to say, you know what, I'm actually only waiting for this guy, so I get to cut the line and, screw user 3. And the point is, it's actually kind of unclear. I don't know what we would do. I'm not a ticket booking site. but I do actually have what I would consider to be a middle ground solution, which I think makes things relatively fair for everyone. Okay, so I guess the issue, more or less, is that we can summarize things like this. You know, if we are allowed to select the exact seats that we're trying to book, you can have complicated dependencies in terms of our queues, right? Because I can want multiple seats, you can only want one seat, but maybe I put that claim down before you did. Who actually wins? It's kind of unclear. So again, the two issues now is that if you were to try and put a claim down on a lot of seats, if it's always the case that you're only allowed to book, you know, if all of your dependencies are resolved, now all of a sudden I want to claim 3 different seats, and that's going to be very hard, so I'm never going to be able to book. Or in the contrary example, where I just am allowed to basically back up everyone else waiting behind me, even though I want 3 seats and I've only gotten access to 1 of them, well, now all of a sudden I'm going to hold everyone else back. So I have this little graphic here on the bottom of the screen just to illustrate that. So let's imagine user 6 is basically going user 6 is going to basically be over here, and it's got claims on all 3 of these seats. And now all of a sudden user 8 is going to drop out. Now user 6 is now first online for seat number 2 over here, and then user 9 is behind user 6. Now user 9 might think, oh wait, I'm second online, I'm actually about to get this thing. But the reality of it is, because user 10 is over here and taking their sweet time, user 9 is never actually going to figure out that they're going to have to wait a while before getting this seat. Maybe they would prefer to get in line for a different seat. Similarly, another kind of bad thing would be, again, user 6 is claiming all 3 seats. User 8 is going to drop out, so user 6 got priority on seat number 2 before user 9 did. But because user 6 is not number 1, right, user 10 is first in priority for seat number 1, user 6 does not have all of its dependencies resolved in terms of making the booking, and so as a result, number 9 is able to cut. So either of these scenarios are not ideal. Hopefully that makes enough sense. So what's another possibility that we could actually do to do this kind of fair claim algorithm while also not either allowing a bunch of people to cut or allowing a bunch of people to get blocked and not figure out that they're going to be waiting for a super long time to hear back? Well, one thing that I've come up with here is actually just not letting users select their specific seats, but rather they would just select a row or a section, and in our back end we assign the user a certain amount of seats based on the number they're asking for, right? So let's say a person comes along and he says, hey, we've got this whole row right here. Here, I'll erase everything and then we can demonstrate it all at once. I've got this whole row right here. These are all open seats, each of these boxes. So user 1 comes along and says, hey, I want 4 seats. User 1 gets there first. Our server says, oh, everything's empty. We can assign you from the left right now. User 2 comes in and says, hey, I want 2 seats. Our server says, okay, that's fine again. I see 2 seats right over here. User 3 comes in and says, I want 3 seats. Our server says, ooh, actually there are only 2 left. Sorry, buddy, you're out. No, sir. User 4 then comes in and says, I want 2 seats again. We say, oh wait, we actually do have 2 seats available. Let's go ahead and book it for you. So again, this is actually going to enable us to get in a situation where we can respect claims that got there earlier first, while also not blocking everyone else, right? Because in this case, even though user 3 was never going to be able to get these seats, they aren't blocking user 4. We can just reject user 3 and then let user 4 book. So again, as long as we process these requests in the order that they're coming in, this is totally fine, and I think it is a feasible enough option. Cool. So the next thing we'll actually talk about is the data model that we're going to be using to do this type of thing. So as you could imagine, because we're trying to implement some sort of waiting list, typically what we want to do is use a type of queue, right? So we can actually take those requests as they come in, and imagine there's a ton of them at a time such that our server can't handle all of them at once. We want to buffer them in some sort of either linked list or a queue or anything like that. So let's implement a queue with a linked list. Why not? So imagine we get order 1, 2 seats. Order 2 with 4 seats is pointing to that. Order 3 with 3 seats is pointing to that. And then order 4 with 2 seats is pointing to that. Now, if our server is multi-threaded, it's worth noting that we are going to have to lock on the last node of our linked list so that we can actually append a new node to the linked list. That's just how it goes when you're multi-threading. And then at least on the right over here, we want to dequeue from our linked list and actually handle, right? We would say, oh, there are 2 seats available, so this is going to user number 1, and this is going to user number 1. And now that that's done, we can go ahead and pop this guy. So another thing that we could also, in theory, do is, we don't necessarily have to process these one at a time, right? We can pop this guy because we know there are enough seats left to handle it. We can pop this guy because we know there are enough seats left to handle it. We don't have to process them completely one at a time. But then once we say, oh, wait, you know what, there are only 2 seats left, now all of a sudden we can't pop this guy. So worth noting, but optimization if nothing else. And then the last element of this is that people are going to frequently want to leave the queue, right? If I've been in for 10 minutes and I don't see myself getting a ticket, maybe I want to go try and book another show, so I say I'm ready to leave this thing. Well, this is where we want to make leaving from the queue efficient, removing a node from it. And so actually one common database data structure and algorithm kind of hack that we can do right here is rather than just using a typical linked list, we can use a doubly linked list with a hash map, right? So now I've got like 1 is pointing here. This is the keys of my map. If it's not clear, 2 is pointing here, 3 is pointing here, and 4 is going to point all the way over there. And so the point is, this can give us removes from our doubly linked list in O of 1 time, because our hash map is going to tell us where our node lives, and then we can actually use our doubly linked list edges to get rid of this guy in O of 1 time, right? We just modify them so that this guy dot next is pointing to this guy dot next. I don't really want to go into this too much, it's going to get messy, but hopefully you understand why these are O of 1 deletes. So we can use a doubly linked list with a hash map. Okay, in terms of expiring unfillable orders, like I mentioned, occasionally we're going to get orders in our linked list which are simply unfillable because there are too many seats left. So what can we actually do to expire them? Well, I would say option 1 is going to be we actually just wait for that order to get to the front of the queue to cancel it. So that's option number 1. And the good part about this is it's efficient, right? I never actually have to like go through the doubly linked list in hash map and remove a bunch of orders arbitrarily from the middle of it. That being said, now all of a sudden, if I've been waiting for 10 minutes in the queue, I actually don't know if it's that my order is unfillable or I just haven't gotten to the front of the queue yet, right? We don't want to actually delay in telling users when their order is no longer fillable, because otherwise they might wait in that line longer than necessary. We should just let them know, hey, it's not going to happen, and then they can get out of there. So that's probably not going to be ideal. I think what would be better is basically whenever we process an order and the number of remaining seats actually changes, then we can go through and expire all of those unfillable entries, right? So now all of a sudden, hey, we've only got 2 seats left. Oh wait, this guy is unfillable, let's get rid of it. Something like that. Cool. So now all of a sudden we have our active order expiration. Like I mentioned, as the number of seats changes, we want to get rid of the nodes that we can't support anymore. So one option, and we're just going to do a little bit of data structures here because why not, is that we do a tree set index of the orders by size. Why do I say a tree set? Well, because, say I want to find all of the orders where there are, where they're requesting more than 2 seats, right? So greater than 2 is what I care about. Then I can quickly traverse this thing in O of log n time. Actually, I suppose it would technically be linear because we could grab up to the entire size of the tree, but the point is it's efficient because it's sorted. And then I aggregate these 2 sets right here, find all sets with seats greater than 2. So that's going to be, or rather find all elements with seats greater than 2. That's going to be these orders right over there. And then I can delete them all from our linked list with hash map. And again, all of those deletes are in O of 1 time. Now, of course, because there are 5 of these, you're really doing 5 deletes, so O of 5 or whatever you want to call it. But point is, yes, it should be relatively efficient from an algorithmic standpoint. That being said, this guy does actually have some cons. Because for starters, now all of a sudden we're augmenting how much storage we need. We need like a secondary index because now we're indexing all the orders by how big they are. And then additionally, every single time that we read this tree right here, we need to grab locks on the actual tree set itself to go and iterate through it. And similarly, that's going to contend with all of our incoming orders, because when we get an incoming order, we have to actually put it in the tree set, and now all of a sudden we have to have locks on the incoming order and actually deleting expired orders, and as a result of that, there's going to be some contention. So maybe it's actually not ideal. And additionally, there's a little bit of time that it takes to go and write an order into this, right? Like if I have another order for size 4 and it's order 10, now all of a sudden I have to put it over here. So I have to find the node for 4, and then I have to add it at the end of the list, which is going to take a little bit. Cool. So what's another option that could maybe be a little bit better is actually going to be iterating through the queue itself and deleting the invalid elements. Right, so the thing is, if there's a ton of elements in this list, that's not ideal, because now all of a sudden every single time that we handle an element, right, every single time that we accept and book an order, we now have to go back all the way through this queue. But at the same time, at least in my opinion, this actually might reduce contention when locking. The reason being that we can basically remove nodes in the middle of our linked list without contending with either the start or the end node, right? Because whenever our handler is pulling from the start to actually process an order, it needs to grab a lock on this guy right here. And similarly, whenever new orders are coming in, it has to grab a lock on the last node in the queue so that it can basically add an edge to that. However, if we're removing a node from the middle of our doubly linked list, we actually only need to grab locks on the 2 nodes that are on either side of the node that we're removing, and assuming that this node is somewhere in the middle of our linked list, ideally the locks that we grab won't have to contend with either the handler lock or the incoming request lock. And so as a result of that, maybe there would be less contention. Again, if we're doing this type of thing like fully in Redis, this is all going to be single threaded, and this wouldn't really be much of a concern. But I do figure that I'll bring it up because a lot of these types of programs are multi-threaded at the end of the day, and when that's the case, you do actually have to think about locking. Cool. So the last thing that I want to mention, or the second to last rather, is actually going to be partitioning. And the gist of this one is that partitioning is going to work basically identically to how we already mentioned it. Again, keeping every single row on the same partition will ensure that if I want to book multiple seats in the same row, I can do so without having to go to multiple different partitions at a time. That being said, of course, there are going to be certain hot rows, right? Like the Taylor Swift rows are going to be a lot more popular for bookings than the Insane Clown Posse, aka Gigolos, if you haven't heard of them. Yeah, those are fun. So the gist is here that, again, if we take those popular rows and we isolate them out to their own partition because we know in advance which ones are going to be popular, that could help us reduce the load on each of these nodes a little bit, maybe mitigate it. The last element of this is going to be data storage. So when I rewatched my old video on TicketMaster, one of the things that I really didn't like about my design was that I actually involved a 2-phase commit, basically from this linked list cache, right, over to disk where we would actually hold the bookings, right? Because every single time this handler runs, it is going to be not only dequeuing something from the linked list, but also adding something to the database. And so that would require a 2-phase commit to keep them completely consistent. Now that is going to be very slow, and when we want to keep when we want to keep this process moving of handling orders, having to do some sort of synchronization over the network is definitely not ideal. So what I propose instead is basically actually using the in-memory linked list and basically a map within that node as our source of truth. So not only do we have the linked list there to store our priorities, but we also just keep a separate hash map of basically the seat to who booked it. And that way we can not only perform replication on this node to another node, but we can also asynchronously send out that data to Kafka and then sync it via a consumer into an actual bookings database. So this is going to mean that all of our historical bookings are within a bookings database, and then basically whenever our seats within a row are completely cleared out, or the event has actually happened, we can clear out all of the state that we've built up in memory, which is going to include the linked list itself, and also just that map of whose seats are actually going to be booked to. So yeah, using change data capture is going to ensure that we don't have to fully wait on this write going to the database before continuing to process more elements. I would think that the combination of the write ahead log, the asynchronous replication to another similar linked list type node, plus the change data capture through Kafka and into the bookings database should be enough for fault tolerance. I suppose that without some form of distributed consensus, it's not guaranteed that we won't lose a single write if this guy were to just get completely nuked forever before one of these guys got sent over. But at the end of the day, it's TicketMaster. It's not life or death. If one booking gets screwed up, they can call customer support and we can always fix it. Cool. So the last element of this problem is actually going to be going through the design formally. So the first thing is that we are going to have some sort of load balancer, right? When the client says, hey, I want to go ahead and book a ticket. And so we're going to hit the load balancer. It's going to direct us to one of the partitions for our order claim servers. Now keep in mind, this is both maintaining the wait lists for every single row, as well as actually storing the information about which seats within a row are going to be booked. So we can partition those on the event ID in combination with the section ID and the row ID. Like I mentioned, just use a hash range partitioning, keep things consistent. And then once we go ahead and get paired up with one of these guys, let's imagine it's right here, we can go establish some sort of real-time connection, like a WebSocket. So that way I'm actually capable of knowing what position in the queue that I am. The next aspect of this is going to be that from here, like I mentioned, we've got some sort of asynchronous replication. Because between a write-ahead log to make sure that if this guy went down, it keeps its state, plus asynchronous replication to basically another kind of waiting queue replica, we can then also do change data capture to sync all of our data onto disk, right? So it's going to put it into the appropriate partition. Ideally, we partition our bookings database by user ID. The reason being that if I'm a user and I would like to see all the tickets that I've bought, it would be great if those were all on one partition. So again, we're just throwing these into a bunch of different Kafka queues. Some sort of consumer is going to be getting those. It'll hit some sort of load balancer to say, oh, I see there's user ID X for this booking. Which one of these database partitions is it going to? And of course, all of these database partitions are themselves replicated. We can just do single leader to keep it simple, just so we don't lose the data. Plus, also, those replicas can themselves serve requests. And then finally, if this guy wants to see, hey, like, why don't we go get my bookings? A load balancer in conjunction with some sort of booking service, right? Bookings service can go reach out to the proper partition of the database and then fetch their results. Okay guys, well it turns out I was able to make it through this video. My voice is hurting a little bit, but we've gotten through it. I hope you all enjoyed it. I will see you in the next one.